Hi, I'm Neil Glover.
I'm Adaptation.
And I'm Corey Ray. We're seniors at Oregon State University, here to talk to you about our senior design project, sponsored by HP.
Let's start off with talking about an overview of our project. The main purpose of our project is to design a relatively low-cost wireless pulse monitoring system. Most conventional cardiovascular monitoring equipment are relatively large and typically involve multiple wires between the user and the display screen. Our device aims to eliminate the need of those wires by replacing them with a small wireless device that can be comfortably worn. The device can be implemented in retirement homes and hospitals, providing users with greater freedom of movement while still being safely monitored. The final version of the device will be designed on a single flexible circuit that can be attached to the user along with a rechargeable battery. Here are some of the customer requirements that the project needs to meet. Wireless communication, reasonably affordable, easy to use, effective, efficient, and safe to use.
Next, I'm going to talk about how we get our data. I'll start with a basic example. Almost everyone has covered a flashlight with their hand before. When the flashlight is focused very near to your skin, some of the light penetrates deep into the tissue, producing a glowing effect. This project uses that same transparent property of skin to measure the heart rate of its user. In this case, the flashlight is actually an ultra-bright LED, and instead of eyes, a sensitive photodiode is used to measure the light reflected back from the skin. Inside any person, there is a dense vascular network supplying oxygenated blood vital for all tissue. A special protein called hemoglobin is used by blood cells to carry this oxygen. When blood rich in oxygenated hemoglobin is pumped through the tissue, it causes small changes in the amount of light reflected back from the LED. These minute changes are then detected by the photodiode and represented in its output current. It is this waveform from which we get all the data necessary for our device. As you can see in this illustration, light from the LED travels through the skin and is then reflected by the blood cells. This reflected light is captured by the photodiode, and that is the basic principle behind our device.
To process and transmit this data, we chose to use the Texas Instruments Bluetooth Low Energy System on chip. Now, there are many reasons why we chose to use this chip, and let me talk about just a few. First off, it's a single chip design, which integrates an analog to digital converter, memory handling, and an RF transceiver, which are all required to process and transmit the user's heart rate information. It also uses a Bluetooth transmission standard, which is common among many consumer electronics. This chip is also very low energy and allows for a maximum current draw of 30 milliamps during transmission, which is much less than traditional wireless technologies. Size was another important consideration, and with a footprint of just 6 millimeters by 6 millimeters and less than 1 millimeter thick, this chip is very tiny, which will lead to a smaller device for the user to wear. Now, once this data has been transmitted, it will be received by a Bluetooth-capable device, such as a laptop or a computer. This processed data will then be displayed in a Bluetooth-embedded device using a graphical user interface, written in the Python programming language.
As you can see from the block diagram, we chose to break our project up into several major functional components. Each individual block represents an independent process crucial to the correct operation of the device. The block diagram is created in such a way that the research and development for each section can easily be assigned to different group members. First, I'm going to talk about the sensor block. This block consists of an LED and photodiode. We chose an LED that emits infrared light at a wavelength of 910 nanometers. This is ideal for our project because at that wavelength, oxygenated hemoglobin absorbs light, while most other parts of the body, such as bone or hair, do not. This allows us to easily focus in on the changes in reflected light generated by the changes in oxygenated blood, while easily ignoring the constant reflections caused by other parts of the skin. To sense these small changes in reflected light, we decided to use a photodiode with a peak spectral sensitivity of 910 nanometers. The photodiode produces a varying output current based on the amount of reflected light it sees. Next, we have the signal conditioning block. Here we use a transimpedance amplifier, sometimes called a current to voltage converter, to transform the small current waveform into a voltage waveform with increased amplitude. This block also keeps the ADC from experiencing the high output impedance associated with the photodiode in the sensor block.
The microcontroller block consists of the TI-CC2540 Bluetooth Low Energy System on chip. The chip's onboard ADC takes the output voltage waveform generated by the signal conditioning block and references this voltage to ground during conversion. A 4 MHz sampling frequency is used, created by the fixed internal timer, and converts this into a binary representation in 2's complement. This converted result is then sent to the ADCH and ADCL registers via the Direct Memory Access Controller. The Direct Memory Access Controller is used to control all data transfers on the CC2540 chip. Before data transfer can take place, the DMA must be armed via the DMA ARM register. The DMA must be triggered by a trigger event set by a software package provided by Texas Instruments. The DMA then transfers the data to the Bluetooth Low Energy transceiver. This is a 2.4 GHz Gaussian frequency shift keying radio with a sensitivity of up to 97 dBm.
Now, let's talk about the wireless receive block. Bluetooth chips nowadays, embedded inside our computers, can receive up to 3 megabytes per second per sending signal via low power radio wave. The receiver or sink reassemble the truncated data. When the sink, say a computer or a PDA, receives the data, the sink device knows which application is going to use the data via the device's ID requested. The request for getting the received data is being sent via the device's ID using an application, say Java or Python GUI.
The data processing block handles the digitized sensor output data by creating an application using software provided by Texas Instruments Software Development Kit. This application consists of 5 major sections. The operating system abstraction layer operates like a control loop, which lets the software set up the execution of events. The hardware abstraction layer provides an interface of abstraction between the physical hardware to the application and protocol stack. The protocol stack is provided as a single library file by Texas Instruments, and the source code is not accessible. The generic access profile layer handles the device's access modes and procedures, such as device discovery, link establishment, and link termination. The generic attribute profile is used by the application for data communication between the 2 connected devices. They are each either in a client mode or a server mode. Our user interface block will consist of a graphical user interface application written using the Python PyQt4 toolkit. Some of the major classes used in the development of the GUI include Qt GUI, Qt Core, QPainter, and QLCD number. This GUI will display the user's pulse rate in beats per minute, as well as a warning indication, such as if the device becomes disconnected.
Now, I'm going to talk about the power system block. This block is comprised of 2 major pieces, the battery and the charging circuit. For our project, we decided to use a 3.7 volt lithium polymer battery, which has a capacity of at least 1000 milliamp hour. We chose a lithium polymer battery because of its size, small size, flexibility, thickness, and ability to recharge. The second part of our power system block is the charging circuit. We are going to recharge our circuit via USB. To do this, we decided to use Texas Instrument BQ24232 IC. This chip provides overvoltage, reverse current, short circuit, and thermal protection. It can handle up to 500 milliamp of input current.
Lastly, we have the frame block. To achieve an ideal hardware implementation, we chose to mount our parts on a flex circuit. Flex circuits consist of malleable plastic layers on which copper traces can be printed. Using this technology allows our device to be flexible and durable, both of which are design requirements for this project. Here's our project timeline. Fall term consists of ordering and testing, then we will build a prototype. Winter term, we will test and refine this prototype and think of possible design enhancements. During the first part of spring term, we will implement these enhancements, and at the end of spring term, we will demonstrate our project at the Engineering Expo.